That's my first chapter of my PhD. I'm the last year of my PhD, and I just have one chapter done. I have more three to write, and like 6-7 months. It's crazy. It's normal for everyone, you know. And this is the first one. I think it's almost done. And the title is Revealing Persistent Impacts of more than 20 years of tropical and forest fragmentation and canopy structure and forest function with LIDAR remote sensing. Okay. So, what is the forest fragmentation? Basically, the forest fragmentation when we leave a piece of forest surrounded for another environment, like agriculture, forestry, or urban. And this another environment change the interfere and the climate in the microclimate into the edge, into the fragment, and this breaks the linkage between the fragments, breaking the flux of animals, flux genetic information. And there's some global estimated for tropical forests in this paper here. There's more than 50 million tropical forest fragments, piece of fragments, an area of 30 million hectares. It's almost 1/3 the area of the USA. It's a lot of tropical fragments. And 50 million linear kilometers of edges. It's important, the edge, because the effect of the edge, we'll talk more about now. Well, what is the effect of the fragmentation? So basically, in this graph here, we have the distance from the edge and two fragments. I put this figure here for we can imagine better what is that. This is the 1 hectare fragment. It's like this one. It is the 100 hectare. It's not this one. This one is 10. Okay, just for imagine. This is the distance for the edge, 0 and 0. This is the edge. This is interior of the forest. And the black lines is the vapor pressure deficit. Ou seja, how say ou seja? It's
in other words.
In other words, it's what's more higher, less humidity, less moisture. And the white one is the temperature, okay? And we can see the higher temperature in the edges for different transectors collecting different times, because there's a little difference of the values. Because the time is different, the days is different, there's different transectors too. And the most happen for 100 hectares. It's important comparing 1 hectare to 100 because there's two effects, basically two effects, the edge effect and the size of the fragment effect. And another effect, when we change the climate, we too open for wind, for other interference. And basically what happens, a lot of trees that fall into this period. There's standard dead trees, probably because because it's dry, less moisture, and the fallen damaged trees because the wind probably. And what we can say here is distance for the edge and the x axis. It is close to the edge, and there's more dead trees, percentage of trees with mortality. And you into the forest for the fragment more than 500 meters, you decrease in the mortality of the trees. This is 10 years after the fragment. The first one this was 6 months after. It's important because the time is really important too. Okay, this is the size effect. We're talking about the edge effect. That's like example of the size effect. And we have the 3 sizes of the fragment and an intact forest, a no fragment forest. And we can see here the mortality and the increase of pioneer trees. This is the density of the trees, but pioneer species. And there's a correlation with whereas the mortality is higher, we have more increase, more incidents, more recruitment of the recruitment of pioneer species. You can see the 1 hectare fragments happen here, 10, and the 100 hectares happen more for this side of the graph, less mortality and less. And this is a global study just showing the biomass, emissions of the biomass. There's some estimations that you can increase like 30% of the increase of emissions of carbon of the atmosphere. But these studies, it's done with satellite images, with SAT, estimation of biomass by G-glass. It's a LIDAR by satellite. It's a low precision. It's not so accurate, but it's happened. Basically, we have some problems with study better of these problems. So this study basically is about the camera is happening anywhere. Oh, it's my camera. No.
There's my cameras here.
Oh, sorry. Okay, we have the structure. Basically, we will investigate these variables. Okay, the canopy height basically is the mean of the canopy. It's the rugosity. The rugosity is a variable very interesting. It's a horizontal heterogeneity of the canopy surface. And the canopy openness, or gap fraction, similar. And leaf area density. Where is the leaves of this canopy structure? More in the upper canopy, middle on the understory. And why you all think these metrics will change because the structure, well, because the fact of the edge and size. We will try to create some hypotheses. And if you want here think different, please say. So this is a moment important. The height. What's supposed to happen with the height? I think the height will be smaller because there's in the edge have a lot of mortality of the huge trees, and it will be the increase of pioneers species. Small. Someone think different? Okay. And the gaps, opening canopy. I think it will be more open canopy, more openness, because the dynamics is higher, and there you have more falling trees, more open canopy. Someone think different? No one? Okay, we're wrong. You're wrong. The rugosity. The height is okay, it's smaller, but the rugosity is the same. You're wrong. I will need to tell about it. But why? We discover why. The rugosity, I think the rugosity will be lower in the edge. Rugosity is really difficult because it can be lower because the mortality of emergent grow trees, huge trees, and the rugosity will be smaller. But at the same side, you can be higher because the gaps, it's different, really no aspect about the rugosity. And the leaf area distribution, my spec is we have more leaf area density and the understory because the pioneers. Make sense? Anyone think different? More leaves and the understory? You're wrong now again. Okay, this is impressive because I really think these things when I start to analyze this data, and when I watch the data showing something different, I think, whoa, it's something wrong. But it's nice when you try to understand why. Okay, but what do you know about the structure? There's some studies already did in the past. Basically, this one, 4 years after the fragmentation, and in this work, he tried to show the distribution of the leaves on the profile. Okay, there's a canopy height, the profile, vertical profile. It is a density of leaves, and this is the density of leaves, and the distance of the edge. When what you can say, there's more in the understory, closer to the edge, more in the understory, and will be more leaves in the upstory. Okay? When you increase the distance for the edge, we have more leaves in the upper canopy. Okay? But this work and this work, what this work show? This work show this small higher. Okay, it's lower high in the edge. This one is 10 years after the fragmentation. But there's some limitations about these works, because these works was made with visual measurements. And I think most of you already went for a tropical forest. It's dimension high of the high, it's very difficult. It's almost impossible. And the leaf area density, it's impossible. Okay, we can do some methods, but it's really difficult. The precision of the cross list is very difficult to know. But I believe in these works, but I just would like to show here, it's very difficult. The accuracy is very difficult. Okay, basically then we have some problems. We will try to solution these problems. The first problem is we need to know what happened along the years in the fragmentation. Because what happened 1 month after, 2 years after, 5 years after, but what will happen 50 years after? We don't know. And because to solution this problem, there's a project in Manaus, the Biological Dynamic of Forest Fragmentation Project. I think it's the largest and biggest study of fragmentation, tropical fragmentation. And this has happened like nowadays is 30 years. This is starting in the 80s. And the data we will investigate work 22 years after the fragmentation. And how mainstream they structure with high accuracy. And nowadays we have the LIDAR remote sensing. I will explain better what's the LIDAR. And we have some sample limitations, no? Because we have to install, to do a lot of plots, but it's very difficult because now in the plots in the tropical forest, in the identification of the species, mainstream the trees, is a limitation for this. And to solution this limitation, we try to link the remote sensing with plots and extrapolate for the whole area. Okay, basically the LIDAR, it's a remote sensing with the near infrared spectrum, and we can know the position of the target, position of the leaves in the wood. It's a 3D data. Here's an example of a big area, and the right is the example just for one tree. Basically, we can see the three-dimensional, the X, the Y, the position, latitude, longitude, and the height, Z. And we use this data, and we use this data too. This is me. It's 4 years ago. And we have these LIDARs. It's very interesting. This LIDAR just mainstream the Z, and the X, I do the X walking in the forest. And basically we have this type of data. It's 2D, it's not 3D, it's 2D. And I walk in and I transect, this is X, and the LIDAR giving me the Z. And basically we use these two remote sensing. This one I used for the height, the canopy openness, and the rugosity. And this one I use to leaf area density, because it's more density. The data is really more density. Okay. So the objectives of this work is investigate the influence of the edge effects and size, the fragment size, and the canopy structure and carbon function of the forest. What is the 4 questions that we have? The first question is about the height. Okay, canopy height. How the canopy height change between the fragments or the continuous forest, no fragment. The second question is how the horizontal structure different in the canopy openness and the rugosity. The third question is the leaf area density, how it's different. And the fourth question is the linking between LIDAR and field data, trying to understand the dynamics of biomass and the correlations between the variables of LIDAR and field data. Okay, the method is it's this sequence, the study area, how was the LIDAR collection, and data processing. Basically, this is the BDFFP, the project close to Manaus. And this is the whole area, but we don't have data in the whole area. We just have data in some farms. And where it was highlighted with these red squares. And you have a fragment here, or the fragment, I will talk more about this after. But basically, we have 51 1-hectare plots with field collection. It's these small black squares, is the plots of 1 hectare. And 3 of these, it's 1 hectare fragment, is this one, and this one. This picture is here is the canopy high model, okay? It's the high of the trees. The blue, it's basically the soil, and the head is the huge canopy trees. And we have more 10, 11, is 11? 12, I was confused, 12 to 20. 12, and the 10 hectares fragments in this one, and this one. And 9 and 100 fragment, it's the bigger one here, it's 9 plots. And 27 and the continuous forest, it's this one, this one, this one, and this one. And we have mainstream all the trees, upper than 10 centimeters. And we have a lot of inventories since the 80s, but it's important we have inventories in this date, because the LIDAR date, we have the same year to collect data. And basically we have 5 to 8 times for each plot in the continuous inventories. And we mention for these plots, the basal area, tree density, pioneer species tree density, the biomass was estimated with the equation of Chaves, and including the dynamics between these variables, okay? Basal area, biomass, the density of trees and species, not species, it's trees of pioneer species. The Airborne was collected in the same year of one of the inventories. These are some parameters of the LIDAR. It's not so important to say now here. And in the 6 fragments, we already said 3 of 1. Always we said the last papers, all the papers in the past said 1 hectare fragments, but now we have the exact point of the GPS, and its cover is not exactly 1. It's around 2, around 10, and 1. It's 99 hectares. Okay. But we have 2 of 1 hectare, 2 of 10, and 1 of 100. The LIDAR was collected 7 years after, in July 2015, and 18 plots. The plots was collected just in the higher fragment, 100 fragment, and this area of continuous forest. Okay, 90 plots here and 9 plots here. And for each plot, this is 1 plot, 1 hectare plot, we have 2 transects. And this transect was parallel for the edge. In this way, we can use each transect for a distance for the edge. Like this example of transecting 20 meters and 80 meters. Okay? Okay, the processing data, we basically use the 3D airborne laser scanner to create the canopy surface and the ground. And the difference of the canopy and the ground, we have the canopy high, it's the height of the trees. We use the resolution of 2 Each pixel here is 2 meters, and the height of the trees. Basically, we extract the 3 variables from the canopy high model: the height of the edges of the fragment, the open canopy. It's how much percent of the pixels is lower than a threshold. In this case, the threshold was 50 meters. We create a threshold of 50 meters, and how much pixels it's lower than 50 meters. This is the open canopy's fraction. We get this variable. And the rugosity, it's the standard deviation of the heights. Okay, is the mean height, the standard deviation of the height, the rugosity, and the how much percent is less than 50 meters. And basically we create by a digital digital draw the fragments, and we create the distance for the edge. And then we have a distance for the edge for each plot. Then in each plot we have the field data, the distance for the edge, and the 3 variables of the LIDAR: height, rugosity, and open canopy. For the ground LIDAR, we basically create this grid and the transect, and with a modeling, a McCartan equation, there's already some papers using this approach, we create the leaf area density, the density of the leaves. And when we sum the leaf area density, what is the unity? It's meter square of leaves and a meter cubic of space. When you sum all of the transect, all of the profile, we have the leaf area index, very famous variable. Because basically we lost 1 dimension, and we have a meter square of leaves and a meter square of soil. Because the leaf area index, there's no unity, because the meter square and meter square. Okay, so basically just recording, we have the canopy height, the rugosity, the canopy openness, and the leaf area density. Okay, let's go to discussion and results to answer these 4 questions. Canopy height difference, rugosity and open canopy, the leaf area density, and the linkage between LIDAR and field data. The first question is, the canopy height is different. Everyone here said, well, it will be smaller in the edge. Yeah, it's right. Look, you have 6 fragments, and all of them start for low high. The Y here is the canopy height, and the X is the distance for the edge. And you can see for the all fragments, they start for the lower high. And basically between 40, 30 meters, we already stabilization here, stabilize horizontal asymptote. And here I just use the plots to compare with the continuous forest, because here there's no continuous forest. But the continuous forest is between 28 meters, the mean, 28 meters, in the standard deviation limits. It's similar for the fragments here. We have some, this is significant here. And I create a model with 3 parameters. Okay, it's difficult to see here, but basically we have the alpha. Alpha is the limit of high, is the asymptote. Okay, it's basically the alpha indicate the height of the interior of the forest, and beta is the intersect of the equation. Basically, this is indicate the height of the edge, and gamma, it's the difference. It's the tax, not tax, the rate of change. Okay, I was significant. The rate of change was significant for everyone. Basically, we have difference for the edge and the interior. and we have the values for the edge and interior to contrast here after to see the difference of fragment size effect. But basically, we have edge effects in all the size fragments. But what is interesting here, when you contrast the alpha is the interior high forest, and beta is the edge high. We can see the smallest fragments, they're small high too in the interior. Basically what happened when we have the whole fragment was affected. Then the higher fragments, larger fragments not so affecting the interior like the small ones. And it's a synergism effect, because the edge of the whole fragments it's smaller too, but it's smaller in the small fragments. The edge is really more small in the small fragments too. It's a synergism effect, okay? Understand? And why it's happened? Okay, we already discussed about that. Basically, what we have here, each graph here, it's a distance for the edge, okay? Here, it's less than 40 meters distance for the edge, 40 to 60. It's a sequence of distance for the edge. And each line here is one plot, and the history, the ages. 18s, 85, 90s, 2000, 2005, 2010. This is the years, and this is what happened with the density of trees in the history of the plots. What's really evident here, we can see the density of the trees because the mortality. It's important to say this, the first inventory was before the fragmentation, okay? And after the fragmentation, a lot of trees die, and recovering like 15 years after this, a lot of pioneers species appear. This happened for some here, but this is stopped to happen from up to 6 meters. There's no more edge effect apparently upper than 6 meters. But basically it's a high mortality and an increase of pioneer trees. It does affect the height of the structure. We already expected that, no? Okay, and what happened with structure? The rugosity is very interesting result here. The rugosity was no different for the smaller fragments, but was different just for the middle size of the fragments, and for the higher fragments there's no effect too. Okay, there's significant, the p-value is significant just in these two cases. And why it's happening? We will discuss there after this other result. The other result is the canopy openness. We suspect the canopy openness will be higher in the edge, no? But there's no difference. Okay? The canopy openness is the same in the edge and into the forest. Why? Why the rugosity just was different in these two? We discussed about that, saying in the small fragments, the whole area was affected. The whole area, the trees died. And because we lost the bigger trees that will create the rugosity, and because the rugosity is the same, because the whole fragment was affected. And you have basically a shape canopy surface. But for the middle fragments, the middle size fragments, there's a buffer effect. The interior of the forest protects the edge, but not too much. And the edge, there's an effect of the edge, but the interior was the same. It was not so damaged. Okay, and because the edge is different for the interior of the forest, we have some mortality of the edge, but interiors which still have some huge trees, emergent trees, because the rugosity is different. And the huge fragment, 100 hectares, the buffer effect is higher. It's like exists the edge effect, but it's smaller the effect. It's not so dangerous, the damage is not so high. And because you still have some bigger trees in the edge and interior. We hypothesize that to explain. And this is a field data for another paper. The last paper was made with this same data, but they start with the 99. We have more 10 years after this paper of data, because I showed these graphs because we have more data. But basically, what they show here is the size of the fragments, but it's number of the near edge, the number of the edges. And here's the mortality, the density, and the richness. And when we don't have edges, basically we're talking about these plots here. There's no edges. And we have one edge, is the 100 hectares, because just then have one edge. When we talk about two edges, we're talking about the 10 hectares, have two edges. And we're talking about 4 edges, we're talking about 1. And basically, this X here is the size of the fragment. He used the number of the edges, but basically it's the size of the fragment. And what you can say here, is there more mortality with the smallest fragment. What was talking about? I already explained this. You just understood what showed the same results, just to support our hypothesis. Okay, and why the canopy opens is not different? Because the time. Look what happened. We lost a lot of density or biomass too, but it's a restoration. There's a recovery. There's a resilience effect of the restoration. And if you have the LIDAR data 5 years, 10 years after fragmentation, probably the gap fraction, the open campus will be different. But 15 years after, not 15 years, 22 years after, the pioneers trees already closed the open canopy, the supposed expected open canopy. Okay, with pioneers trees. And about the leaf area density, basically we have the canopy height here and the leaf area density, the distribution, and the sum. It's the leaf area index, but when you sum this, you have this line. And the leaf area index, it was the same for all of them, the edge, for the distance for the edge, the color's distance for the edge, okay? But the distribution was different. And we expect there's more leaf area density in the understory, but no, it's smaller. It's contrasting the paper what we saw in the introduction. There's 2 papers, 10 years after, and 5 years after, and both of these studies show a different result. This is very interesting. It's basically, it's the age it happened, no? Because I think it's one of the evidence is important to investigate many years, long years after the effect of fragmentation. And there's more leaf area density in the middle of the understory. And the upper understory, of course, there's less. It's correlated with the high, but there's more in the middle. And why it happened? Probably because the pioneer trees what grow, nowadays it's in the middle. It's not more so small trees. Now it's happened in the middle. And they close the understory. There's not so much more growing trees in the understory. These trees what grow in the past was mainstream 5 years and 10 years after for the other studies. Now it's the middle of the canopy. This is our hypothesis. And basically you can see the test of the leaf hour index was not significant. The leaf hour index for the understory was lower and the edge. And the middle, the two structure of the middle was higher, the leaf hour index. Basically, it's the sum, no? The leaf hour index is the sum of this. Okay. This segment, perfect. And the upper story. The upper story aspect, we have less leaf hour density. Okay. And how the LIDAR metrics was linked with field data. Then we have here, the biomass was a good correlation with the canopy high. Makes sense, no? And the rugosity, there's a good correlation with the basal area change or the biomass change too. But why? Because the plots were lost biomass. Bigger trees die, and the rugosity was small nowadays. You can imagine. In the past, we have huge trees, emergent trees, and these trees fall. And now we have the restoration of other species, and the rugosity is small. And we lost biomass. And these two graphs here is just to explain what was expected. The change of the trees 5 years after is correlated with the canopy high. When you have the lose of the trees, the canopy high is smaller. In the past, when you loses the tree, and the other side, you increase the other species, the pioneer species, and the high is smaller too, when we have more pioneer species. Okay, we have more pioneer species, and the same plot, we have more mortality in the past. The other paper, Flowers, 2006, showed the same results. But nowadays, we're working 10 years after with LIDAR data correlating. And here, we estimate the biomass for the whole fragment because we have the data, just the field data. The pink, look just for it, you know, we're talking about that one after. The pink here is the field data. And the box plot here, it's the estimation of the biomass with LIDAR and the confidence interval by a bootstrap from this model here. And it's interesting because in the whole all the fragments, the pink line touch the box plot. The larger pink line, it's the median, okay? It's the median. Touch, and here almost don't touch. Probably because the sample here is smaller, no? Because in the one fragment, it's one hectare, 2 hectare, 2 hectare, 3, 12, 40, 14, and 100. And 100, we have just 9 hectares sampled in 100. Here we have the whole, almost the whole. And what's interesting here, there's no effect because the biomass recovery. We saw that. No, the biomass recovery after the years. The biomass the same. But we can't. You could see effect of the edge, and this effect we just could solve with the LIDAR data. There's no effect when you use the field data because we have more. The sample is bigger. Now we have a grid. The whole grid and estimation, we can compare it. And this black line is 100 fragment. This blue line is the other fragments because the slope of the models was different. And the X here is in log, okay? It's a no linear model in the case here. Okay, we can talk more about this after the presentation of some questions. And basically the conclusion is, we have persistent effects. It's always changed. 22 years after, we still have effects for the size, for the edge effects. And the LIDAR data could improve the estimations of biomass and the correlation. We can basically use the LIDAR to extrapolate the field data, which is already shown in a lot of papers, but no, it's the first one in the fragmentation, in the tropical forest. And there's a resilience in the biomass. It is very interesting because there's a lot of spaceborne approaches. There's a lot of studies using spaceborne and with this resolution of 30 meters or more or less resolution, no? And how say about the edge effect with a resolution of 30 meters? With the edge effects happening in 30 meters. And because it's important, the LIDAR too, because even the plot is 100 for 100, is 1 hectare plot. And we believe the size of the plot can interfere for the results, no, if you don't have the... Okay, basically, it's that. Thank you.